Okay. So good afternoon to everybody. I think we can begin now. Okay. We are a little minutes late, but we will recover at this time. So welcome to Assisi. I'm very happy to be here with in a meeting in presence with you in Assisi. And it is the GAM, so it's the General Assembly meeting of our project, no? Clean HME. So first of all, I should apologize because it was programmed planned to have an entire day for our meeting, but it was really impossible because many Italian colleagues told me, the majority of, I can say all of them, told me that they prefer to vote in the morning, and so it was possible to have the meeting only in the afternoon. This is the situation, you know that. So there was some difficulty to organize the meeting, but we have the structure of the meeting is the same of the last years. I mean, the majority of the time, most of the time is employed with the scientific lectures, and the last part, 1 hour officially, but I think that we have other possibility to meet during the workshop, and is devoted to organization and administrative problems. Then I can say that we have 3 very nice lectures. The opening one is given by Jean-Paul Biberian, which is very well known, of course. Then we have another lectures of 45 minutes by Andras Kovacs. And then another interesting lecture by Dr. Jacques Rouet. So we have 3 lectures, and then we have a time to have the general discussion. I say, even if I know very well that it is very early. We will have very soon. We will have an important meeting, a review meeting, and then I think that most of the time will be devoted to this problem. Okay, then I have to say that we will have a break at exactly at 4:30, half an hour of coffee break. And then there is the last part of the meeting. Second part of the meeting will be chaired not by me, which I'm the host person in some way, but by Professor Chersky, who is the coordinator of the project. I have not other to say, if not that I thank all the people that helped me to organize the Claudio Pace, who is Dr. Claudio Pace, who is also a hosting person here in Assisi, who is present, I think, and Dr. Montagnoli, Francesco Montagnoli, who is a collaborator at the Politecnico di Torino, and Domenico Scaramozzino, who is also a collaborator of my group. Then I can thank also other people, of course, Dr. Collis, that is the main organizer of the next workshop on anomalies, etc. You know him very well, and I think that I have to thank also Professor Chersky for the help in organizing this meeting, of course. Thank you very much, and now I introduce Professor Biberian for his lecture, please.
Okay, thank you so much, Alberto, and thank you for this invitation. So it took me a while to figure out what shall I say. And then I thought about we should go back to the past, because a lot of people here are new in the field. I mean, new means 10 years, 20 years ago, you know. The field is 33 years old, so they're new to me. So I was thinking maybe I should talk about the past and see what has been done in the past. A lot of things have been done already. But before starting, I don't know how to use this computer. There's the mouse here. I want to have an introduction. Why hydrogen is a crucial element? Because when you have an atom of any type, you remove an electron, the ion will be about the same size as the atom. But if you remove an electron from hydrogen, you end up with a proton or a deuterium, which is 10 to the 4th to 10 to the 5th times smaller. So there is a major change in the fact that you ionize hydrogen. So this is why hydrogen is so important in cold fusion. And without hydrogen, there would be not much going on, you know. So I think everybody knows that, but it's good to remind it to people. So now, let me go. Problem with aging is that you have to put glasses on and off, you know. Anyway, summary. I will talk about our two heroes, which are Fleischmann and Pons. They did a very amazing work at the very beginning, a lot of work. And most of the work has been ignored, forgotten, you know, so I want to remind it. Now we go to the searches for nuclear ashes. Obviously, if you have a reaction, you have an ash somewhere, something, so we have to find out what is this ash. Then I talk about nickel-hydrogen system, which came later on, but not so late after the discovery of cold fusion. Then I want to talk about nanoparticles, why they are important. And I have a paragraph on theories. I think there are close to 100 theories, you know, so they cannot be all good. Probably they're all bad or partial, something like that. We see. What about the future? And the journal. We have a journal, so we want to talk about it a little bit. Fleischmann and Pons work. They have done a lot of work. They started in 1985. Even though they went public in 1989, their work started 4 years before. They did it with their own money. They spent, at that time, $100,000. So it's a lot of money from their own pocket. I guess they are rich. They could afford it. And they did a lot of things, and then they went public in 1989. And here are the picture of these two guys at that time. They are older now. I mean, Stan Pons was born in 1943, so he's 79 years old now. Fleischmann died in 2012. Unfortunately, he's not there anymore. I mean, Stanley Pons worked in Utah at the beginning. Then he moved to France, south of France. He worked there until 1996, if I'm not mistaken. And then he left the field completely and he didn't do any more research on cold fusion. And by the way, I had a great chance to be a friend of him. And one day he called me and said, take all my equipment. So I had my car, the trunk of my car was full of materials, electrodes, metals, all kind of chemicals. And so I got all this equipment from him, electronics. I mean, the trunk was full of equipment. So I still have a lot of his equipment. And then, let's see. If you can read, I have to put my glasses on to read it.
You want to have closer?
No, that's okay. I can move it. Yeah, I can move it. This is part of their first paper that was published in 1989. The establishment of negative overpotentials on the outgoing interface of palladium membrane electrodes for hydrogen discharge at the ingoing interface demonstrates that the chemical potential can be raised to high values. Our own experiments with palladium diffusion tubes indicate that values as high as 0.8 electron volt can be achieved readily. Values as high as 2 electron volt may be achievable. The astronomical magnitude of this value can be appreciated readily. Attempts to obtain this level via the compression of D2 would require pressures of excess of 10 to the 26 atmosphere. So this is very interesting. What they do, what they say, when you put hydrogen in the metal, you change the potential of this electrode. And the overpotential, that means the level of potential change, can be correlated to a pressure. So that's a Nernst equation. I will show you after that. But what's interesting in this first paper, they show only the first two reactions. They don't talk about the helium production. They ignore completely helium production because the ones that are known were really affecting fusion of DD is not the one with helium-4, which is rarely produced. So I wanted to point it out that they were not expecting helium-4. They were expecting tritium and neutrons. So what's the Nernst law? Nernst equation. Nernst equation is an equivalent between the pressure outside the system and the overpotential inside the system. It's called fugacity because it's not really a pressure, but it's equivalent. So that means if you have an overpotential of 0.8 electron volts, that gives you equivalent pressure from the outside, which are huge, I mean, astronomical pressures. And I guess their first idea when they started, I mean, you never start a reaction for no reason, you know. They were thinking about that, so they were hoping that putting a very high pressure, they will squeeze the deuterium and create a reaction. That's why they did the experiment. It turns out that very few neutrons and very few tritium. This is one of their, in the first journal, first paper, the measurements. They have done a lot of experiments with a lot of different electrodes. And they got excess heat. I mean, these two guys are extremely careful people. I talked to them. I've done experiments with Georges Longchamp at the end of the 20th century. We repeated Pons-Fleischmann experiments with the same cells that they gave us. We have the original cell. It carries 2 cells from them. And we never managed to have as much as they did because they are extremely careful about cleanness, about everything. Even though Longchamp was very careful, we got some results, but not as good as their results. Anyway, you have the excess heat with different electrodes, diameters, and then they've done one with a cube. Why did they use a cube, 1 centimeter side cube? Because the currents are focused at the center of the cube. So they imagine that doing that, a sphere would be even better, but it's hard to make a sphere. So a cube, if you have a cylinder, along the axis of the cylinder, that's where all the current is concentrated. But when you have a cube, you concentrate at the center of the cube, which is much better. That's what they did, and they had an explosion. A few years ago, when I talked with Stan Pons, I met him at his house, and I said, okay, you have the hole. How big was the hole? There was a lot of discussions about the size of the hole. So he said, he showed me with his hands, that big and that deep. So it was a big hole. It's not like something simple. It was really a big thing. So they were really afraid of that. That's why they don't advise to continue in that direction. Okay. That's what, I mean, when you get something like that, you might be thinking maybe something is happening. Now, they measured also neutrons and gamma rays, because they were looking at this equation I showed you before. And they thought they had gamma rays that could explain production of tritium and neutrons. There was a lot of controversy about this spectrum, because some people said they are not correct and anything like that, but they had something with gamma rays and showing gamma rays and neutrons. But the quantity could not explain the amount of heat they had. So they say there's something else going on. They didn't mention production of helium-4, but in the text, they said something is happening, we don't know, another mechanism. It's not this one. This is a cell. It carries 2 cells. It is a very simple, I mean, if you look at science and discoveries, people have made discoveries by making their own instruments most of the time. It could be a bubble chamber, a telescope, James Webb telescope. I mean, that's not a small thing, $10 billion to make one. But with that instrument, you can see things that you cannot see with your bare eyes. So anytime you want to make a discovery, most of the time you cannot buy it on shelf somewhere and use it. You have to make your own. And they were really good at making a calorimeter, very simple design. It's a double wall test tube, basically, with vacuum between the 2 walls. And they have there are electrodes, which is at the bottom, the cathode. It's a, usually they try different sizes, diameters, and stuff like that. The standard is 12 millimeter, half an inch, by 2 millimeter in diameter, wrapped with a anode, which is a platinum wire around it. And they even, I mean, I have some discussion with mice because he didn't know about that, but it's off axis. It's not in the axis, because by doing off axis, the bubbles will go up and down, it will just mix the liquid. That was a smart idea too. Later they didn't put it on the side, but they did it. I have the cells, so I know it is off axis. Then you have a temperature sensor, and they also have a heater so that they can put heat on the system to see what happens. And this is very important because the system works better at higher temperature. So by pushing the temperature of the cell higher, you get better results. This is, they discovered something very important called heat after death. In this curve, you can see the temperature going up. I mean, I don't like times in seconds. It's hard to read that, you know. I like hours or minutes or days, but not seconds. I mean, this is the worst. I mean, in our case, if you make a 100-meter race, you better use seconds, but in that case, seconds are not useful. Anyway, this is a legal number. You see the temperature going up. At one point, the cell is half full. That means usually in their experiments, they keep on adding water because of dissociation of the water. So they have to add some water regularly so that to maintain the level, to do good calorimetry. But in this experiment, they stop putting water in it, so it will go dry at one point. So the water will go down and down and down, it will be dry. So there's a first line where you see the cell is half full, and just after that it's completely dry. And there's no more water in it. There's no more water, no more power active inside, and the heat continues. So they call it heat after death. For those people who believe into reincarnation, that's part of it. Heat pulses. This is very important. I was mentioning that. You see the curve, the base curve, you can see the temperature, and when they add the heat pulse, the curve doesn't go back to the same level as it was before. It goes a bit higher. That was an indication for them that something was happening. Because if you do that with a platinum cathode instead, it will go back to the normal level. But with the palladium, it goes up higher. So they used to have regularly pulses like that to increase the temperature, the output power. Obviously, this is subtle. But you have to be a good scientist to see the subtleness, you know, that nobody else sees. You know. For someone else, it's just like an error. But for them, it was really something important. Then they realized that boiling becomes very important. Now, there is a discussion at the moment about flux. When you have your cathode, the hydrogen ions are coming to the cathode, but the cathode is not uniform. There are places where you have more current than other places. So when you have more current, there are more hydrogen going inside, but they will go out somewhere else where there's less hydrogen. So you have a dynamic stability, but locally there is a change in hydrogen, or deuterium in that case. If you have reached the bubbling, if you have bubbles, it's even worse. Because when you have a bubble on the cathode, the current cannot go through. It's a gas. So locally, you decrease the amount of the current. If you decrease the current, you deload. So you have deloading one place and loading the other place. So you say some dynamics going on. That's why they showed some experiments. I showed you before, when you go dry, you have more heat when you go to boiling. So they designed a new reactor, Icarus 9, which is so that you can have continuous boiling, so that the water is up. I mean, okay. It is a Pyrex tube. At the bottom there are the electrodes, and the whole thing is in water at constant temperature, and the water vapor condensates on the top and goes down, back down. So by measuring the temperature at these different levels, they can calibrate their system. So they have done that, and they have shown that it can produce a lot of heat. That was, look at this is the carrier 9 cell excess energy with time. Look at the time. It's a lot of hours. So it's a long experiment. So there's nothing at the beginning, and at one point it starts going up and up and up and up. There's a lot of energy being produced at that point. That was a paper published at the conference in Japan in 1996 by Stan Pons. Unfortunately, Stan Pons is a very shy person, not very good at public speaking, so he spent a lot of time explaining the calibration of the system, and people didn't realize the output of the system. A few years ago, I asked Stan Pons if I could have another Icarus 9 cell. He said, I don't have one. Everything was at IMRA, and I don't know what happened to the material equipment. Probably they threw it away. I mean, there's no use. But we got the drawings, and we found the person who did the actual manufacturing of these cells. So I have 2 copies of this Icarus 9 cell in my lab. But I was not good enough to do the experiment correctly. I hope to do that one day. Anyway, that's interesting work. This is a picture of me with the 2 heroes. So I'm not an hero, but I'm next to a hero, so that maybe it just transpired. I don't know. Who knows? That was just before, a few months before the death of Martin Fleischmann, and the other one, it was in 2013 at Pons' house. Okay, now let's see for nuclear ashes. How far am I in time? Well, I have to speak more faster. Nuclear ashes. Okay, we can have heat, that we know, helium-4, helium-3, neutrons, alpha particles, tritium, gamma rays, X-rays, transmutations, radio frequencies. I mean, I don't think I missed anyone. Maybe if you think I forgot something, you might tell me. So let's see, heat and helium-4. I think there are many, at least 6 or 7 people have shown production of helium-4, maybe more. But I like the SRI work because they used a gas loading system developed by Leslie Case. Leslie Case is an engineer, chemical engineer. He knew a lot of catalysis. And he took a box, filled it with a standard catalyst that he bought, put hydrogen, deuterium, pumped it, cleaned it, did a lot of things, and finally got excess heat. So at SRI, they tried to do it. It didn't work. It didn't work. So they asked Les Case to come to SRI to do the experiment with them. So it did the experiment there, and they measured the helium production. And they have a correlation between helium and excess heat that could be equivalent to 23 mega electron volt per atom. So that's for confirmation that could be helium-4 production correlated with the reaction. Arata. Arata is a very interesting person. He unfortunately died a few years ago. He developed a cell, I will talk it later. But anyway, in his experiments, he found helium-3. There are very few people that measured helium-3. I mean, at SRI, they also measured helium-3. When they send their sample to there are very few labs capable of measuring helium-3 with a mass spectrometer. They saturated the mass spectrometer. I know there is a lab in France that can do that, but very few labs can do good measurements of helium-3. Now, neutrons, very, very few neutrons. I mean, I think it's a good thing, but there are very few neutrons. So one way of finding neutrons is to use, because there are so few that if you measure it with a spectrometer, the flux is so low that you are in the background. But there's a material called CR39, which is a piece of plastic, and when a a neutron reaches that, it makes a very tiny hole in it, and when you etch it in a basic material, it was, what one was it? Sodium hydroxide, I think, at 70 degrees or something like that, the hole becomes bigger. So you can detect neutrons that way. So they've done a lot of experiments with co-deposition at the Navy in San Diego, and they found neutrons many times. So we have neutrons, very, very few. You cannot explain the excess heat. Claytor measured tritium also. Claytor was working in Los Alamos. I mean, they love tritium there. I remember at the conference at ICCF 24, Storm said, why don't you measure tritium? I said, but I never worked at Los Alamos, so how can I don't even know how to do it. Anyway, they know how to do it. And they found tritium by doing discharges in hydrogen, in deuterium, I'm sorry. And I asked Claytor, I mean, why didn't you convince people that you were producing tritium? He said, because it didn't work every time. So when it doesn't work every time, it's hard to have someone come and see your experiment. But you have to make sure it works. Gamma rays, here, Piantelli detected gamma rays with a nickel film on where it was and hydrogen. So there are gamma rays. Again, there are very few. So we have them. X-rays, oh, okay. X-rays, we know there is no hard X-rays. If there are very few. But there are probably soft X-rays that don't come out of your cell, of your reactor. So what Violante did, he used a thin film cathode. You see the design is horizontal. And underneath he put his detector. So he could measure some X-rays. Not much, but he could measure some. So there's probably some X-rays produced, but low quantity and low energy too. Transmutations. Well, there are quite a few papers on transmutation. I want to show you Miley's work because he's done an experiment where he showed that they analyzed almost all the elements of the table, you know, and they saw peaks, which has also been reproduced by Mizuno, similar peaks, where you see transmutation. Now, doing mass analysis is a headache, especially if you have to look at too many elements because they overlap on one on top of the other. You have to be very, very careful with these measurements. But there are definitely transmutations. I can show you this one. Yeah. This one, okay. I will talk about it later also, but Fralick at NASA in 1989 wanted to find neutrons and gamma rays and stuff like that. So it took a hydrogen purifier, which is mainly palladium plus silver probably, and he borrowed it from a friend of him and put deuterium in it, heated it up, and put all these instruments around waiting for production of neutrons or gamma rays. Nothing happened. A few weeks later, this guy said, I want my purifier back. So what he did, he pumped out the deuterium, and at that time he see a temperature jump. Didn't make any sense. When you pump, you should cool down. So he tried it again. He tried with hydrogen. Hydrogen cools down, deuterium goes up. And recently, they took this purifier and analyzed it under a electron microscope to see if there were some transmutation going on. And this is one of the craters showing there's transmutation locally at different points of the sample. Radio frequencies. There's only one person I know who's done a lot of work on radio frequencies, is Schwartz. Schwartz looked at the radio frequency emission, and he found very precise lines. The problem is Schwartz papers are so hard to read that I gave up, you know. But if you have courage, you can read them to understand what he's doing. But we have seen radio frequencies also. Now, what about the nickel-hydrogen system? Schwartz has done electrochemistry with nickel hydrogen, and he's found there's a loss of deuterium. He measured the amount of deuterium there is in the light water, there is deuterium in light water. And he saw a decrease of the deuterium. That means deuterium, maybe the little bit of deuterium there is in light water is active. I don't know. Anyway, he's done very good work on that. There's a lot to do about nickel hydrogen. Anyway, nanoparticles. The first person who started working with nanoparticles was Arata. I met him in Marseille in 2004. He went to the ICCF 11th conference. And I asked him, can you give me one of your cathodes? He said, no, you cannot have one of my cathodes because you're part of NATO. Later on, he collaborated with SRI in America, but I was French. I don't know why he said that, but that's what he said to me. I'm part of NATO. He's a very smart person. So what he designed is he designed what he called the double cathode, which is what he did. He specialized in welding palladium. It's not easy to weld palladium. So we took a palladium bar, made a hole in it, filled it with palladium black, welded it, even did experiment. We put a pressure gauge to measure the pressure increase when the current deuterium goes inside the cell. So he did electrolysis that way. So what happens, he dissociates deuterium that goes inside the walls of the chamber, of the tube, and then goes inside the powder. When I was with Longchamp, we got a patent from him in Japanese, and we got a translation. But in English, palladium black means powder. But they translated palladium black by palladium and carbon, coal. You have to be careful with translation, especially from Japanese to European languages. So we couldn't understand why there was carbon in the system. There was no carbon, so it was just palladium black. But that way, he could load the palladium black with not hydrogen molecules, but hydrogen ions already. So he could, and that way he could get excess heat. So he has done experiments. He has put two cells, identical cells, one next to the other, one with hydrogen, the other one with deuterium. And he's doing heat flow calorimetry. Flow calorimetry with water cooled. And you can see here, this is the one slide I like the most. On the right side, you see hydrogen, there's nothing, and the other one is deuterium, and you see after, if you can read the numbers, in hours, a lot of hours. Slowly start going up, and as time goes by, it's almost exponential. And when he has 24 watts, you wonder why he stopped the experiment then, because the cell exploded. That's the only reason he stopped it. It's not that he wanted to stop it, but the pressure was so high. As I was telling you, there is a correlation between the overvoltage and the pressure. So he was building the pressure inside the cell by this way. So it's a proof that there is a correlation between the two. Then he decided that if powders are important, why don't we use directly in gas phase? So he developed a system where he used these nanopowders made by melt spinning. They take an alloy of palladium and zirconium, make an amorphous material by cooling it, by dropping it in a wheel, cooled wheel, and then oxidize it and so on and so forth. So he made this thing, he put hydrogen in, deuterium in it, and he got excess heat. And you can see the particles of palladium, which are about 5 nanometers in diameter. So this is very interesting because he's the one who initiated nanopowders. Theories, I know people will. This is the one slide that I hesitate to show. Okay, there are many theories. I made categories. I don't want to go in each category, but you have electron screening. That one I like the most because it's very simple. I understand it. Resonances, there are all kinds of resonances. heavy electrons, because we have muon catalysis, muon fusion, you know, which is called cold fusion, by the way, where a muon is being 200 times heavier than the electron. The orbit of the muon is 200 times closer to the nucleus, so you can have fusion reactions. This is well known. It has been studied, but you have to produce muons, and they're expensive to produce, so the thing is not really reliable. You cannot really use it commercially. And also the reaction, when you do the reaction with muons, the byproducts are the same as hot fusion. It's not like cold fusion. You say you get the neutron, the tritium, and everything. So, but some people have tried to find situations where the electron become very heavy, and you can have fusion. Okay, phonons can have magnetic monopoles, believe it or not, but they exist. It seems you can invent new particles, like the Hertzion. You can have polyneutrons, and so collective motions. I like that one too. So the one I like is the first and the last, actually. Electron screening and collective motion. Maybe both are used, I don't know, together. Though I'm not going to say words on theories. I don't understand them. It's too complicated, so I do experiments. Now, the theories are more likely interested in finding the solution to have the reaction to occur. Now, what happens to the excess heat? How does it go away? I mean, the only person I know who did some work on that is Peter Egelstein, who thinks he has phonons. And these phonons are dissipated in the crystal. But there's something I like better. In a chemical reaction, when two hydrogen atoms react to form a hydrogen molecule, the energy of formation is about 2 electron volts. I don't know the exact figure, but roughly that. So H plus H give you H2 plus 2 EV. But however, there's no emission of a 2 EV photon. In fact, there's emission of many photons of lower energies, totaling 2 EV as a total. Hamed Zewai is an Egyptian chemist. He received the Nobel Prize in Chemistry in 1999 for his work on femtochemistry. That's how he proved that the emission is not 1 photon, but plenty of photons. So it seems to me that when these two ions are getting together, because it's slow motion, cold fusion is slow. It's not like high energy physics. So they go slowly, 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 and so they might lose X-rays, soft X-rays. I don't know how soft it is, but soft enough that they don't come out of your cell, of your reactor. Is it time now? What time is it? Well, I have to finish. Huh? I'm getting there.
5 minutes.
5 minutes? Okay, I'm doing pretty good. I still have 16 slides. Anyway, so I believe into soft X-rays. Future. Okay, we can have all kinds of activation mechanisms. Temperature, electrical, acoustic, pressure, flux, magnetic, whatever, name it. Temperature. Okay, I've shown you that with Ponce-Fleischmann work with pulses. We know temperature plays a role. But I think temperature alone, in this case, it's not temperature alone, because you have also a flux of a deuterium atom, a deuteron inside the cathode. But in nanoparticles, we have in a different situation where you can have collective motions, maybe of hydrogen or deuteron inside the crystal. So maybe that's why it's interesting to work with nanoparticles and not with solid materials, unless you put an excitation. Storms have shown the effect of temperature on the results. I have shown it also. Temperature goes up with temperature. You can even calculate the activation energy and so on and so forth. So we know temperature has a great effect. Electrical, I like the work of Dardik. Dardik is an MD, medical doctor. He's not a physicist. And he was training the US Olympic team with super waves by playing with the frequencies of movement or whatever. So they applied it to cold fusion, and they got good results. Instead of sending a DC current in the cell, they send this kind of current. You can see there are all kinds of frequencies together, low frequencies, medium frequencies, high frequencies. and that way they could get good results. That has been done, and it works. You can have, so acoustic excitation. Stringham has done a lot of work with acoustic, with the piezoelectric systems when he has heavy water, and they use targets made of silver, palladium, different materials. And this is one of the holes is produced on a silver foil. Magnetic, this is my work. I published recently at the conference where I have rotating magnets. And this is very interesting. It is at room temperature. And the temperature inside goes up to almost more than 40 degrees above the room temperature. By just rotating the magnets at a frequency of about 3 Hertz and using nickel powders, nickel materials. I will write a paper on that. It's not as simple as that, but there's something going on with nickel and hydrogen and magnets. The flux, Fradic, I was talking to you about Fradic at NASA. This is his hydrogen purifier that he used. In 2012, he repeated the experiment. The first one very crude, but this one he made good measurements. And you see when he loads hydrogen, temperature goes up, that's normal. But when he deloads with hydrogen, it goes down. Whereas with deuterium, it goes up when you put the pressure in, but it goes even higher up when you deload. We remove the deuterium. So there's something abnormal there. Lee did very good experiments also with the flux. So he took a palladium tube, filled it with deuterium, pumped it on the outside, and he could show you the comparison between the flux and the excess heat measured. So I've done something similar years ago. Same thing, a tube. I was putting deuterium pressure in it. I was pumping it out. This lasted for several days. You have excess heat every time. The problem is that you use a lot of deuterium because you keep on pumping it. Now, let me say a few words about the journal. At the beginning of cold fusion, people could publish papers, especially negative papers. People love the negative ones, but positive ones a little bit more difficult. There were a few journals that were publishing these results because editors-in-chief were in favor of cold fusion. In particular in France, Jean-Pierre Vigier, who is a theoretician, physics, he was the head of physics letters A, so he published many papers on cold fusion. But it turns out that it is very difficult to be active in this field if you cannot publish. So in 2003, no, I'm not finished. Oh, well, forget about this one. It's just a mistake. In 2003, we had a meeting, ICCF 10 in America, and we had a meeting, and it was decided to create the society we are organizing at the moment, organizing this meeting, and a journal. The first editor-in-chief was Peter Hagelstein, but after a few months or a couple of years, maybe he said, I give up. It was too much work. He was not ready to do it. So he gave me the stick. So now I'm an editor of this journal. So we publish papers. We publish many papers. And since ICCF 16, we publish all the proceedings of the conferences. So they are all in one place. So it's good to have that in one place. The thing is, at the moment, this journal I'm doing the work. I mean, I have referees and stuff like that, but everything is in my computer. I have backup on my computer, but that's not a problem. And one day I will leave this earth and the whole thing will be lost. So we are planning to work with a society, external society, where the journal will be located. So it will be better for the future. For the person who will take over after me, it will be much easier than finding things in my computer. So thank you. Any question?
Oh, thank you very much, Professor Vibert. It was a very very comprehensive overview of this matter. Oh, thank you very much.
Thank you.
Now this lecture is open for discussion. We have about 10 minutes. If you want to put the question from your chair,
Okay.
Otherwise you can come here.
Okay, no problem. Just very simple question. How much the cost of Scholastica for typical numbers of paper published in your journal?
I think I
For
don't
each
have-
year, just to have
Yeah.
an idea, how much?
I'm doing this work with Katinsky, and he has the right figures. I hope I have the numbers, but it could be around 3,000 euro a year or something like that, or less. It should not be that big. Euro, dollars, whatever, you know, pounds, anything. Not liras. Yeah, yeah, but maybe it will be less than that. It will not be too expensive. Yeah, maybe. Yeah, more or less. But they will not do the editing work. The editing work is separate. It's made in India. Dr. Kumar was doing it for a long time, but unfortunately, at the time of COVID, he died of COVID, and we are really in a bad situation. We tried to find someone else to do it, couldn't find it, and finally, his son is doing it. So he's not as good as his father, but he's doing the job anyway, so he's learning. I mean, Indians are smart people. I'm not worried about that. They know how to do things.
So the total price, 5,000.
Yeah. Yeah, it will be less than 5,000 altogether. So far we have the money to start with, for the first year, with no problem. We have the money for that. Some people gave money. But we can find money, I'm sure.
So another question, please. No questions or
good.
discussion? So I can put a question.
Yeah, good.
Yes, I was impressed by the list of characteristic phenomena that you gave in your lecture, because usually anyone speak about one of the characteristics of characteristic phenomena related to cold fusion, usually. So maybe for me it's the first time I see all of them, you know, so it was very interesting. And then I was moved to put to you a question. So you think they are characteristic? You maybe the list was about 10 or 15 characteristic phenomena, and you think there is a more or less a strong correlation between them or not? Because also in your case, I think there was a very complete list, but without any attempt to correlate them. So I was impressed by also, it's not negative, but more positive also.
No, you're right.
So I want to ask you this very general question.
That's why I did this presentation, because you are not the only person who didn't know all that, you know. I mean, I'm old. Yes. I studied more than 30 years ago to work on cold fusion, so I had time to accumulate all kind of knowledges, you know. Anyway, yes, there is probably a main reaction, especially with deuterium, is production of helium-4. But then plenty of side reactions, which are not very important, but they exist anyway, like transmutation, like
transmutation is very
like
important,
all kind of grays.
Important?
Yeah, it is very important,
very
but it's not the main reaction. There are other reactions.
No,
it's not. I think it's secondary
reactions.
I think so, because
You are
the amount of material that being produced cannot really compare to the amount of heat produced. So I doubt. But
yes.
again,
No.
I'm not God, so I'm not sure.
It's an assumption.
It's an assumption.
I
think it's not. Because you see, if you look at helium-4 production and the heat produced, there's good correlation. That means probably the best, the good material. But again, this is true for deuterium. Now for hydrogen, I really don't know. I don't know what's happening with hydrogen. I wish I knew. The only thing I know, I didn't put that, but my friend Mastro Matteo is here. He's done this experiment with laser beam, and he has shown transmutation with hydrogen and palladium. So something is happening with hydrogen and palladium. With hydrogen and nickel, we have a lot less information. But I have repeated this experiment and found the same result as he has obtained. So, I mean, at least been twice done. So I think something is happening with hydrogen, but what is the main reaction? I don't know. Transmutation there is, but I cannot explain. I don't know.
And then you know that Storms, in
Yeah.
his very famous book, he says that cracking, micro cracking, is very important because he says that it is the environment or the location of learner, no, of learner. So what do you think about that? Because maybe it's the only one that you didn't report in the list.
No, because, well, he has done a lot of things. So I could,
You know that I work a lot on fraction.
I know. The fraction is a different story. I think it's very interesting. But is it the same mechanism? I don't know.
It's not correlated, you think?
It's not, I don't know.
It's
if
micro
correct.
cracking, intense
Micro
micro
cracking,
cracking in
maybe
in
you have
the
electric
electrodes.
field.
No?
Yeah, I know, with electric fields.
Not only me, but also
No,
Storms.
Storms also. I know. There are plenty
You know
of
that
things.
I
mean,
think is the
there are
fundamental point.
many points that I don't understand, you know.
No, but it's
I
a very
see.
complex
It's extremely
picture,
complex.
very complex,
Yeah.
complex. But I think that we have not, but because I have this experience of about 15 years now, I think the fracture, micro cracking, or even at the nanoscale, not only for micro, but also nano, is very, very important. Maybe the origin of everything.
I mean, I know you
I
work
think
on earthquakes,
Yes, also.
production of neutrons, so...
And earthquakes, you can think that there is very big faults.
Yeah.
But the reality, the real thing is that you have a multi-scale phenomenon. So you have from nano to the tectonic scale. Yes.
Yeah.
So it's very complex. But I think that are very correlated phenomena. This is my
Okay.
very deep conviction. Well,
I think
anyway,
Conrad wants to ask a question, yeah.
excuse me. Yes.
Yeah. Jean-Paul,
Please,
you
please.
have so much experience in the field. You worked for 30 years in this field. So my question is, from your point of view, we should think or should understand the processes of this. Oh,
Yeah. That's
you
okay.
can hear me, yeah?
Yeah.
Okay. So if you want to understand what is going on, we should think about a very simple process at the moment for the first. And if in the case of DD reactions, it is most important thing that we can try to understand, and you can fit some models for that. It is branching ratio. If you speak about production of helium-3, helium-4, neutrons and protons, what is your opinion? What is the branching ratio between different channels? We know what kind of channels can be produced, you know. So how much helium-4 will be produced? It depends on material or depends on something else? Or you understand your
Yeah,
opinion,
I understand. No, I mean, when I talk about palladium and deuterium, I think the main channel is helium-4, but no gamma rays. It's probably soft X-rays. That's my belief. Now, the other channels, neutrons, very few, tritium, very few. Probably there's some side reactions, but they're very limited. Now, this is true for palladium and deuterium. Now, for the other reaction, I have no idea. I mean, I wish I would know. I was hoping to find something we didn't find yet. I want to see that with nickel and hydrogen. I wish I will find one day what's going on with hydrogen and nickel. It's a lot more complicated. Hydrogen is not a good candidate to do cold fusion. I mean, it makes sense, you know.
But in the case of nickel, do you see some differences between deuterium and hydrogen, so protons?
I've not done enough work on that. As far as I know, from the point of view of Iwamura and also Takahashi, they seem to say there's not much difference between the two. But it's something I have to look at. I have to check that. I don't know. You know, I mean, our experiments are not reproducible to the point you can see small differences, because reproducibility is not good enough to see a few percent variations. So if the variation is small, you will not see it. If the variation is an order of magnitude larger, that will be easy to see. But I've not seen that so far. But I don't know. But you're right, we don't know. I mean, the nickel is interesting because it's a ferromagnetic materials, and I could show in one of my talks, I didn't show it here, but ICF-24, when you rotate the magnets with a nickel filled with hydrogen, you don't have a heating effect, you have a cooling effect that lasts for days, you know, not like a few seconds, it lasts for days. You have cooling of maybe 10 watts or more. Doesn't make sense to me. I mean, how can you have cooling effect? I mean, I was hoping to have heat and have cold. So I was planning to propose it to NASA because they want to send something on Venus. They need a cooling there because temperature is so high. But there's no application at this point. No, but how come we have cooling? Doesn't make sense at all. But we can see it on the curves. As soon as you reach the Curie temperature, the temperature jumps, you know. So there. So I don't know. There are many strange things. I've done some surface analysis of my nickel after the experiment. I've seen a few things, but nothing significant. It could be pollution, it could be contamination. It's hard to say. And to be clear, it should be necessary to do isotopic analysis. But isotopic analysis, it's easy on paper, but it's not as easy in real life, you know. In real life, it's a mess, you know. You have interferences all the time and things like that. It's hard to conclude. So, okay, maybe
thank you very much. Thank you very much. Let us thank Professor Ribera for his excellent lecture. So now we have a second speech or lecture by Andras Kovacs. Please, the title, I don't have the title with me now, but we can read, I think, very soon.
This one, yes. The question, is there a pointer? I don't know.
Il pointer, quello di, diciamo, is the light, you mean the light? Ce l'avete la luce, il pointer, ce l'avete? Ce l'ha lei?
No, this is fine, so I can use.
Is it fine?
I think I can use.
The arrow, you mean? The arrow, yes, yes.
I mean this mouse.
You can use the arrow, I think.
Yeah,
Yes.
I can use
It's very effective also, yes. Thanks.
Okay, so
Please, you can speak.
Yes, the title of my presentation. Okay,
Yes,
now, yes.
Microphone.
Yeah, so my presentation is about the discovery of the nuclear electron, which is a big step forward in nuclear physics, and then I will talk specifically about how that relates to our work. So first I start with the science history context, and I don't see the slides myself on the screen, so that's why sometime I will be looking back. So our... no, here I don't see it on the screen. So anyway... oh. Yes. Yes, our story begins with the discovery of the neutron in 1932. At that time, nuclear physicists were split into two camps. One camp, which included, for example, Heisenberg, was claiming that the neutron is a small hydrogen-like particle. And the other camp, which included Pauli, claimed that the neutron must be an elementary particle. So a few years later, Chadwick's group was successfully photodissociating deuterium, and upon its photodissociation, they found that it always, in their experiments, splits into a proton and a neutron. And upon learning this news, that it always splits into a proton and a neutron, the majority of the nuclear science community at that time decided that Pauli's view was right, so the neutron must be an elementary particle. And at that point, the nuclear electron idea was dropped. So we can see that this is a watershed moment in a way in the science history, and that's why in the presentation I will be spending some effort to understand exactly what happens in deuterium photodissociation. So now this consensus about neutron being elementary particle lasted only 5 years, because in 1940 Alvarez group measured the neutron magnetic moment, and that started speculations that the neutron must be some kind of a composite particle after all. So there were next 30 years various neutron models circulating, and in 1970s the quark model became popular, and that is the model that remains popular to this day. And so when I was presenting some aspects of my concept previously to project colleagues, some people told me that there's a difficulty to concentrate on my experimental data because the quark theory is so good. So now in my presentation I will focus on experimental data, but to get the right motivation I have a few slides about the assumptions behind the quark theory, which I will quickly go through. So the basic assumption behind the quark theory is that both proton and neutron each comprise 3 fractionally charged quarks, but these quarks are always observed in the bound state. So in that way, quark proponents tell experimentalists, don't bother looking for quarks, you don't find them. Okay, so how do they think then quarks exist? The idea is that they can be seen in high energy proton-electron collision experiments. These are called deep inelastic scattering in the physics language. And the idea of these experiments is the hypothesis that if the electron flies energetically enough into a proton, then it will scatter not off of the whole proton, but only from a subparticle of the proton. So to construct the statistics of these subparticle scatterings, experimentalists use the so-called F2 function, which maps the statistics of the momentum exchange as a function of the mass fraction of the particle. So here the x is the proton's mass fraction. And there you can see on the chart the original F2 data that has not been adjusted in any way. So Gell-Mann's prediction was that the peak must be at x equals 1/3, which corresponds to 3 subparticles. And what you can very easily see is that Gell-Mann's prediction is wrong. So this mismatch between prediction and experiment then necessitated a second assumption, and the second assumption is that there are not only 3 quarks, but also there is a sea of virtual quarks and gluons, and those cause this mismatch. And after fitting all the parameters, quark proponents suggest that the actual mass of the quark is only 2 to 3 megaelectron volts, so very small fraction of the proton. Okay, then we have these 2-3 megaelectron volt point-like quarks, and we can calculate their magnetic moment with the well-known formula for the magnetic moment calculation that you can see there. And then you get a mismatch of a factor of 100 with respect to the proton's magnetic moment. Okay, so then that initiated another assumption that quarks have 2 types of masses. So one mass is the naked mass that you see in the inelastic collisions, and the other mass is the so-called effective mass. And this effective mass is about 340 megaelectron volt that is showing up in the magnetic moment measurements. Okay, so then we have this effective mass. So we take 2 such quarks and form a pion, for example. Then the pion mass must be about 700 megaelectron volts. Okay, so now we again have a mismatch by a factor of 5 with respect to experiments. So we need yet another assumption that these effective quark masses are very particle specific. So in every particle you have a different type of quark mass. Okay, so we have these quarks with highly variable mass, that 3 of them are moving around in a proton or neutron, and they always result in a constant magnetic moment. So why is the magnetic moment constant? Why is it not adding up with different vector angles? So then there is yet another assumption, fourth assumption, that, actually it's already assumption number 5, that the 3 quark spins are isotropically correlated. It means that they're always aligned in the same direction. Okay, sounds logical assumption, but it was pointed out to quark proponents already in the 1960s that this assumption seems to violate the Heisenberg uncertainty principle. And to get around that, Oskar Greenberg introduced yet another assumption that quarks have also so-called color charge. And again, they told experimentalists don't bother measuring it, we will never measure it, but the color charge is there, and then that removes this problem with the Pauli exclusion. Okay, so does it really work? Does this color charge assumption remove the contradiction? So I recently published a book with some co-authors, some of whom are in this room. And in this book, we dedicate one chapter to the analysis of Pauli exclusion principle. It was written by Paul O'Hara. And Paul O'Hara's derives mathematically that 3 particles can never be in isotropic spin correlation, because that leads to a mathematical contradiction. And his proof is actually quite straightforward. It's less than 2 pages, so I can send it to anybody who is interested to read it. And what this means is that there is still a contradiction with Pauli exclusion principle regardless of the presence or absence of color charges. Okay, so we have this long stack of assumptions that finally lead to a mathematical contradiction. I think rather at the end, because otherwise we get into long discussions. Okay, now let's see what the quark theory says about the neutrons. So according to the quark model, neutron decay starts by the ejection of an 80 gigaelectron volt particle that is 80 times heavier than the neutron itself. So that's quite a magic trick. It's like a magician pulling out an elephant from the hat. And but there is no experimental evidence for this assumption either, which means that these 80 gigaelectron volt particles have never been observed in neutron decays. Moreover, what is important to realize is that there is experimental counter-evidence. So let's consider an interesting isotope, the decay of dysprosium-163. So this is stable as a neutral atom, but when it's stripped of all of the electrons, then it becomes a beta decay isotope. So now let's start with this stripped dysprosium-163. So it is beta decaying, which means according to the quark model that it produces these 80 gigaelectron volt particles. And according to the theory, the production of this 80 gigaelectron volt particle is completely independent from the electromagnetic environment. I should not care about the presence of orbital electrons. But if we add orbital electrons, then we can see that the beta decay stops. So it means that actually the electric voltage is the control parameter. And this is, again, a contradiction with the theory. So this clearly shows that there cannot be any 80 gigaelectron volt particles produced in this process. Okay, so after this very quick theory overview, I hope that everybody is finally interested in and has motivation to look at the experimental data. So now I will focus on the experimental data after these motivating slides. So one very big set of experimental data is the map of nuclear isotopes, where with each isotope it has been mapped out what happens to them eventually. So in this map, it's like a periodic table of isotopes. On the vertical chart, you can see the charge number, and on the horizontal slide, you can see the difference between the charge number and the mass. So in this map of isotopes, you see in the middle this black line, that is the line of stability. These are the stable isotopes, and what you can see is that if we move from any direction from this line of stability, we end up either emitting electrons or absorbing electrons. So the set of these many isotope experiments shows that any displacement from the stable position means either electron emission or electron absorption. So it's a quite straightforward idea that there must be then some negatively charged components to the nucleus. So we will, inspired by this experimental data, we'll explore this idea and start to look for their signatures. Now the first way, or the first perspective how we look for their signatures is via the consideration of electrically neutral particles. So if there are inside the nucleus these negatively charged particles, they can combine with the positive particles to form electrically neutral ones. And well, the most simple combination is of course a negative particle, which I will call nuclear electron in this lecture. And I emphasize it's not ordinary electron, but it's a distinct particle. And when it combines with a proton, then that's what we normally call a neutron. So this is the simplest one, and one of the next simple one is when you take an alpha particle and add two of these loosely bound nuclear electrons to it, then you can see a mass 4 neutral particle, but I emphasize that this is not 4 neutrons, because what the real structure is that it has an alpha particle core with 2 loosely bound nuclear electrons. And this is an interesting construction, so if it exists, that's one signature for nuclear electrons. And let's consider whether we have experiments that support this. So this first experiment that I discussed is a NASA-funded study where the researchers irradiated with 2 megaelectron-volt photons various deuterated and hydrated materials. So you can see up there the reference paper where this data is from, and these deuterated and hydrated materials were in a lead chamber. So here I focus on the gamma spectrum of the lead chamber itself, which received the same kind of gamma beam. Now they had various research runs, various radiation runs lasting a few hours, and this spectrum that you see here shows 2 runs, but they were not the first runs, so there were preceding runs before these. So the red line, or the red chart is one of the runs, and then the green one is the next one. So in the red one, what I want to highlight is here. Lead 210 isotope that they had in the beginning. This is an artificial isotope of lead, so this was artificially created by a preceding run. So what you see after the next irradiation is that this lead 210 disappears, and instead what you see appearing is lead 214 and its decay product bismuth 214. So this is very peculiar. How did lead 214 transmute into lead, how did lead 210 transmute into lead 214 without any of the intermediate isotopes? So normally, if you had a successive absorption of neutrons, you should see in the spectrum also lead 211, 212, 213, but these are completely absent. Another problem with the neutron transfer is that 2 mega electron volt is actually not enough energy to strip a neutron from any of the lead isotopes. So there is, it looks like you had a sudden jump of increasing the mass number by +4. Okay, let's see how this could have possibly happened. And what 2 mega electron volt is enough, you can see there an exemplary reaction, is to split an alpha particle and 2 electrons from some lead isotopes. And this is energetically possible. So then what is a logical conclusion for how to explain this strange experimental result is that this gamma irradiation must have stripped what I call a dark hydrogen. Dark helium. And why I say dark helium is because it's actually an atomic particle, so it's a neutral particle that doesn't have any spectral lines. So this alpha with the 2 nuclear electrons has been stripped and transferred to another lead, and that made this jump from lead-210 to lead-214. Also, you can notice that all of these artificial lead isotopes, they never decay by neutron emission, so the way they decay is by emitting an alpha particle and 2 electrons. So this reflects the structure of the particle which they have received. Okay, well, this is one experiment. Let's see if we have a confirmation of the same process in another type of experiment. And the experiment I consider next is a very large-scale experiment. So let's think, where else do we have this environment of having few mega electron volt gamma rays and heavy materials? Well, one place is nuclear reactors. So in the nuclear reactor core, we have every day a very large experimental setup with a similar environment than what was in the NASA experiment. Okay, now normally what is the traditional understanding of transmutations in nuclear reactor cores is that there are neutrons flying around, and these neutrons can be absorbed by uranium fuel. So the main isotope is uranium-238. When it absorbs a neutron, it becomes uranium-239. That turns into plutonium-239, and then successive neutron absorptions can lead to plutonium-242. So in order to go from uranium-238 to plutonium-242, you need the absorption of 4 consecutive neutrons by the same nucleus. So as you can imagine, this is very, very low probability in the beginning of the life cycle. However, if we now consider the process which I just introduced in the previous slides, then by the absorption of dark helium, if it exists in this reactor core, you could have a single-step jump from uranium-238 into uranium-242, which then very quickly decays into plutonium-242. So that could be a more probable process. And now let's see what the experimental data shows. So here I have the article reference, which is sampling and analysis of a very large number of nuclear reactor core materials at various stages of the burnup. I think they analyzed more than 20 different reactor cores at various burnup rates, so very extensive work. And what they found is that regarding plutonium-239, its concentration was the same as predicted by the neutron absorption calculations. So that shows that the neutron absorption model was correct. However, for plutonium-242 that I just introduced, they found that in the initial stages of the burnup, its concentration was 3 times higher than the neutron absorption calculations. So it means that there must have been another process which has produced plutonium-242 than just successive absorption of neutrons. And this I consider as the signature of this electrically neutral dark helium transfer, which is in turn the signature of nuclear electrons. As you go to the higher burn-up rates, you can see that both plutonium-239 and 242, they go towards the predicted concentrations. So it means that when the probability of 4 consecutive neutron absorption is high enough, then we get the predicted concentration. So in other words, the concentration of neutrons is much, much higher than the concentration of dark helium, but this chart in the beginning shows that it nevertheless exists in the nuclear reactors. Okay, so this was the first type of perspective on the nuclear electrons, and the next perspective I will discuss their presence during nuclear fission reactions. Now, the traditional view of nuclear fissions is that nucleus during fission splits into 2 fragments, accompanied by possibly some release of neutrons. Now, if we consider also the presence of nuclear electrons, then it's possible that some number of nuclear electrons could be also released as a prompt electron release during fission. Even some protons could be released as well. So we will consider this very general approach to fission and look for some experiments that fit this more general pattern. Okay, the first one that I consider is the fission of beryllium-9. So this is a quite light isotope. And here you can see on the graph the first 3 excitation levels of beryllium-9. And in this isotope, any of these 3 excitation levels, they fission apart the beryllium, so it never goes back to its ground state. Now the first one and the third one, they split the beryllium into 2 alpha particles and the neutron. However, for the second excitation level, what you find in nuclear data tables that it goes into 2 alpha plus neutron only 7% of the time. Okay, what is the reaction in the other 93%? We will find out by the process of elimination, which means that we'll consider all possibilities. So the number of possibilities is limited because it's a light nucleus, and we have to remember that lithium-5 or helium-5 does not exist. Another possibility would be to split into lithium-8 plus proton, but that requires more than 16 MeV energy, much more than the excitation state. So by the process of elimination, the only process which is feasible here is to split into 2 alpha particles, a proton and a nuclear electron. That's going to be the outcome of the 93% of that excitation state. And so I emphasize this is not speculative, but this is the only possibility when you consider all the possible combinations of how it could decay. So that's then a very direct signature of the prompt release of nuclear electrons, which means that they must have been present in the nucleus to begin with. Okay, the next one, now it's more close to our field, is the experiments by Professor Cardone's group, who have ultrasonicated an iron-based bar. So in this bar, it contained 92% iron by mass in the beginning. And after some time of ultrasonication, on the surface, those spots appeared that you can see here. And the authors measured the concentration of elements in these spots. So they found that it's 45% iron, 29% oxygen, and 20% carbon. So these masses quite well add up to the original mass of the iron content. So it does look like we are looking at the fission of iron into lighter elements. Okay, what is, and again, you can see there on the bottom the journal reference where these results have been published. And it's very clear that this is not a some kind of contamination, but these are real surface features. Also, what is interesting is that they have been monitoring the neutron spectrum during the sonication, and they observed excess neutrons during sonication in the mega electron volt range, which is again looks like some kind of fission feature, but these neutrons have been at very low levels. So similar to what Jean-Paul said, just a little bit above the background neutron level. Okay, so we have some kind of a fission which was mainly neutronless. And if you consider that iron has iron 56 as the main isotope, if it splits into carbon and oxygen, then there you have the scheme, how it splits. So it can split into 2 oxygen plus 2 carbon. And yeah, so the masses add up nicely. And if you split according to this scheme, where you have the 1-to-1 molar ratio between carbon and oxygen, it means that the mass fraction between the carbon and oxygen should be a 4-to-3 ratio. And that 4-to-3 ratio is actually very close to the 29% oxygen and 20% carbon that they measured. So it looks like the experimental data is very much aligning to this scheme of the fission. However, when you consider charge conservation, then the charge conservation requires that 2 electrons are also emitted during this fission reaction. So you just add up the charges of oxygen, carbon 2 times, and then you see that there is 2 missing electrons to get to iron. So this then again quite direct experimental evidence that some kind of electron-like particles must have existed in the iron to begin with. Okay, so the summary of these fission-related experiments. So these experiments that we briefly reviewed demonstrate the presence of electron-like negative particles inside the atomic nucleus, and they can be released during fission event. And upon their release, their lifetime must be very short, otherwise we would have observed them already quite a lot, but non-zero. So very important point that what could happen during this non-zero lifetime to these particles. Well, as any other particle, they could undergo quantum mechanical state changes, and one quantum mechanical state change that we'll shortly look at is the possible nuclear reabsorption of such a nuclear electron. So every quantum mechanical state change generates single frequency gamma radiation. Jean-Paul gave the example of hydrogen to hydrogen atomic fusion, but in that case you have a rotovibrational spectra that is involved. But if you talk about a state change of a single particle, the nuclear electron state change, that it must correspond to a single gamma peak. Okay, so we will shortly look at that. And now we will focus on the actual mass measurement of these nuclear electrons. And I will show 3 independent methods for how we can measure the mass of these particles. So the first one is the most simple nuclear process, the decay of the neutron. And here on the chart, you see the energy spectrum of the decay products of the neutron. So you have electron, proton, and neutrino radiation that are, sorry. So you have the neutron decay products are electron, proton, and neutrino radiation. And here you see their distribution of the energy. Now, one person told me that this looks like a 3-body reaction because you have 3 outputs. But actually what is very important to realize is that from the point of view of momentum conservation, this is a 2-body reaction between proton and electron. So why do I say it's a 2-body reaction? Let's consider the case where all the energy is taken away by neutrino radiation. In that case, the corresponding proton momentum is 0, and the corresponding electron momentum is 0. So it means that neutrino radiation carries net 0 momentum, because it does not give any momentum to neither the proton or the electron. Similarly, if you look at the other end of the spectrum, where there is no neutrino radiation, in that case, all the momentum is carried away by the electron and the proton, again a two-body reaction. So from momentum conservation point of view, we have a two-body reaction here, and we can then write the momentum conservation equation, which you see on the bottom. So the momentum of electron going one way equals the momentum of the proton going the other way. And after squaring this equation and some algebraic rearrangement, you can see that the mass ratio is equal to the inverse of the energy ratio. Now, during the decay process, I wrote it as a tunneling reaction, where you have the nuclear electron and the proton moving apart and tunneling into the new state. So the mass ratio actually reflects the mass of the nuclear electron and the proton in this process as they move away at the beginning of the neutron decay. So when we characterize the energy ratio, the most probable value is the value at the peaks. So we can take the ratio of the peaks as the approximation for the most probable or most characteristic values. And here you can see that on the last bottom line, that when you look at the ratio of the kinetic energies, then you get the ratio between the proton mass and 3 times the electron mass. So this indicates that the nuclear electron must be approximately 3 times heavier than an ordinary electron. And that's, of course, why it's an unstable particle and will decay into normal electron. Okay, so next I will discuss the experiments by the Focardi-Piantelli group. So one experiment they had, where they had an iron-chromium alloy that they subjected to the hot hydrogen flow. And on the surface of this alloy, they observed transmutation reactions, so that you can see on the chart there. So the horizontal axis is the distance along their material, and then vertical you see the concentration of the elements. And you can see this inverse correlation between iron and chromium. And at the beginning, at x equals 0, is the original concentration of this material. So this inverse correlation means that iron must have transmuted into chromium, and that means, as you can see, that the chromium concentration indeed goes up from its initial value. So if you write the corresponding equation, then it's iron to chromium plus alpha particle. So it's some kind of fusion-like reaction. So when they made a similar experimental setup, but now using nickel material, then they observed some release of neutrons by neutron detector. So this similar experimental setup suggests that, again, they had some kind of a fission reaction that is also corroborated by the neutron release. Now, what was very interesting in this experiment is that they saw a gamma peak at 661 kiloelectron volts. Now, one person told me that maybe this gamma peak was just cesium-137 contamination, which has a similar gamma peak, but there are two reasons why that could not have been the case. The first reason is that the authors of this article, which you can see on the bottom, they explicitly said that there was no cesium-137 in their lab, so it could not have been contamination. The second reason is that you see here this series of measurements in consecutive weeks, and the intensity of the peak goes down at a rate that is very different than the half-life of cesium-137, which is about 80 years, if I remember correctly. Also, one of my co-authors, he told me that he was at the Focardi-Piantelli lab during this experiment, and he saw on the instrument himself this gamma peak. So I think we have every reason to believe that this was a real signal. Now, what could be the origin of this mysterious signal? So remember, we had some kind of a fission-like reaction, and now our hypothesis is that we have some nuclear electron release during these fissions. So what could happen with the nuclear electrons? The most probable reaction, if something happens with them, is that they are reabsorbed by another nickel atom, nickel nucleus, and nickel's main nucleus is nickel 58, and that is capable of absorbing nuclear electrons. So let's consider what happens during ordinary electron absorption versus nuclear electron absorption. So in case you have an ordinary electron absorption, you start on the left side with normal electron mass plus nickel 58 mass, and then you end up with cobalt 58, plus you need some energy, the electron capture energy, which is actually negative because you have to accelerate the electron to get in there. This electron capture energy is minus 381.6 kiloelectron volts. Now you can consider what happens in case of nuclear electron absorption. So you start with nuclear electron mass on the left, plus nickel 58 mass. You again end up on the right with cobalt 58, plus you have some binding energy of this process. Now you can take these two equations and you can subtract them. So the nickel 58 and cobalt 58 masses subtract, and what you end up with is that mass energy balance equation are right there, that the difference between nuclear electron mass and normal electron mass is a difference between binding energy and electron capture energy. So if we assign this gamma peak that we observed at 661 kiloelectron volt to the nuclear electron mass, that corresponds to its quantum mechanical state change, then the only unknown we left with is the nuclear electron mass. So from this simple equation, we get the nuclear electron mass is 1,554 kiloelectron volts, which is very close to 3 times the electron mass as we have expected. Okay, now I introduce a similar experiment in this kind of perspective. Oh, okay, I will. Really? Okay, I will try to speed up. So I'm sorry I slipped with the time a little bit. Yeah. So I will try maybe in 10 minutes. So in our experiment that I did in the past with collaborators, we created artificial lightning, which means we had spark discharges across water moisture environment. Why did we do that? It has been observed that there is a neutron emission during ordinary lightnings. It has been quite well studied. You see references on the bottom. And this neutron emission has been identified from the reaction of nickel 14 to nickel 13. So this is some kind of a strange nuclear reaction, and we try to see what would happen in this case. If we consider it as some kind of a simple fission, maybe we could also have a prompt release of nuclear electrons during this process. So in our experiment, what we measured is a gamma peak during this very simple setup at 260 kiloelectron volts. And you can see that the use of shielding was essential to get a good signal-to-noise ratio. Okay, with Gaussian fitting, the exact value of this gamma peak is 259.6 kiloelectron volts. And with the oscilloscope, we could see the time correlation between the gamma peak and the spark discharges. So it means that this corresponds to some very short-lived particle that is generating the gamma peak right after the spark discharge. Okay, so we make the similar consideration as before. In our environment, we have only air and water mist. So the only electron-capable nucleus is actually the proton. And we use exactly the same equation like before, mass-energy balance. But now, instead of the nickel-58, we use the proton and the corresponding electron capture energy. And the nuclear electron mass that we get is 1,553 kiloelectron volt, almost exactly the same value as before. So our conclusion is that the mass of the nuclear electron is the average of these two, so very close to 3 times the electron mass. Okay, now I have a third method of measuring its mass, but I have to skip it because of the shortness of time. I received very interesting data from a scientist called Vladimir Nikitin, who has been studied in bubble chamber particle creation processes, where he created particle-antiparticle pairs upon high-energy photon irradiation. And upon analyzing his data from this track of the intermediate particle, you can see it's a 2-step decay. And I have to skip explaining this calculation, but we know the geometry, we know the magnetic field, and from all these parameters, it's possible to calculate the mass of the intermediate particle, and we got 1.6 megaelectron volt mass, which is very close to the mass of the nuclear electron. So I think it's a high probability that the intermediate short-lived particle we see on this track is the actual nuclear electron that we are looking at. And what is interesting from this is that its decay time indicates the half-life of this particle, which is 10 to the minus 11 seconds. So this very short-lived particle in the free particle state then suggests why it has been never observed in previous experiments. But the very peculiar thing about it is that it's somehow stabilized in the nuclear environment, and we have to understand why that is the case. Okay, now I have some slides about deuterium dissociation. I have to unfortunately skip it because of shortness of time. So I have analyzed different processes during dissociation. There is a photoelectric process, Compton scattering, pair creation, and I have calculated the probability of these different processes. I have to skip explaining the calculation, but the result is, you can see there with the blue curve, the cross-section of the photodissociation cross-section of deuterium, and the orange curve of the bottom is the photoelectric effect that corresponds to splitting deuteron into 2 protons and nuclear electrons. So if you're interested in the calculation details, I can send you by email. But the point is that in the 1930s, nuclear scientists assumed that this orange curve would be orders of magnitude higher than the blue curve, because they thought that this high frequency radiation would kick out a nuclear electron. But they did not do this calculation because there were no computers at that time. Today we can do it, but as far as I know, nobody has done it before. And upon doing the calculation, you can see that the real result is actually the opposite than what they expected, that the orange curve is 2 orders of magnitude lower than the blue curve. So there was no real reason why the concept of nuclear electrons should have been rejected at that time. Similarly, I consider Compton scattering, and I have to skip the calculation details, but you can see that Compton scattering, it kicks in above 3-4 megaelectron volts. So in the energy range where Chadwick was experimenting at 2.6 megaelectron volts, there is no Compton scattering either. So now we can finally understand why why Chadwick's group only saw proton and neutron as the output products, and why they never saw actual electrons from the irradiated deuterium leaving. Okay, so now, if I may, a few minutes, I would like to talk about phonons and what phonons have to do with this. So I hope Professor Carpentieri will excuse me for
the question time.
yes, it will be last questions. So here I summarized a few experiments that show the relevance of phonons to nuclear reactions. The first one on the upper left is the experiment of Carbone's group that we already discussed, where ultrasonication was creating the phonons that then caused these fusions with the spitting out of nuclear electrons. Other interesting experiment is the electrolytic palladium deuterium experiment by Michael Schwartz. So he made a Raman spectroscopy of his electrode, and in the active mode, he saw this anti-Stokes line, anti-Stokes peak, that was not present in the inactive mode, and the anti-Stokes peak is a signature of acoustic phonons that were only present in the active mode. Other famous experiment is experiment by Dennis Letts. He also experimented on electrolytic palladium deuterium, and he used laser illumination to activate the reaction. So here you can see the excess power versus the beat frequency of his two lasers that he used for the illumination. And you can see that the peaks appear at a certain frequency levels that correspond to the resonance of energy transfer between the laser and the crystal lattice. Also, what you can see here, that the excess heat versus frequency is roughly linear if you match it. So that means, if the linear match is correct, that you need at least a terahertz frequency to observe anything nuclear. So, what these experiments suggest is that phonons have some kind of an initiating event on nuclear reactions that then cause the spitting of nuclear electrons as well. So now more about this laser illuminated photon generation. This is the experiment by Ubaldo and Jean-Paul. So replicated experiment. Down there is the reference. So after a long laser illumination, which generates photons at the illuminated phonons, then you can see that there is a transmutation spot at the illuminated beam. And what you can see is that the original material remains pure palladium, but in the illuminated spot, palladium almost disappears, and palladium seems to have fissioned into lighter elements. Now, in the original palladium, the ratio of neutrons to protons is about 4:3. In the produced lighter elements, this ratio is about 1:1. So we have a lot of neutrons that have disappeared. Okay, if they have been just released, then Jean-Paul's reactor should have become radioactive. As far as I understand, it did not. So it means that the main reaction pathway must have been the release of nuclear electrons rather than the release of neutrons in this case, and that was the result of the phonons action. Okay, another experiment now.
Excuse me, otherwise we have no time.
Yes,
for
yes.
questions.
Okay, so now, now I think I will have
You
to,
have to go
to go to the conclusions. So I wanted to introduce Professor Carpentieri's experiment, where the fractions were generating terahertz phonons again, and so there is neutron emission, but I have to skip explaining it. So I wanted to analyze the transmutations, and again, there is signatures of nuclear electron release in these surface transmutations, but okay, I have to go to the conclusions now. So sorry about being over time. So conclusions, phonons at or above terahertz frequency, they may trigger nuclear fission reactions, and this seems to be a key process to understand what really happens there. Now, what experiments show that besides neutron emission, such fissions also release nuclear electrons. And also what is experimentally relevant, but I did not have time to go into it, is that this is a surface phenomenon. So these transmutations, they appear always on the surface, not inside the material. So if you have something triggered by phonons that appears only on the surface, it seems that it's related to the reflection of phonons. And that's a big question, why the reflection of phonons? I have some thoughts in our book that I write about that, so you can ask me more details if you're interested. And thank you very much for the attention.
Okay, thank you very much. Thank you very much for your very nice lecture, Dr. Kovacs. Now we have about 5 minutes for questions or comments. Please.
So my problem is you haven't presented any experimental data that uniquely support your idea about a nuclear electron. It is in contradiction with many theories, physical theories. The question is how you want to construct this. This new particle you want to have, or this deeply bound electron by proton? What is it? This new particle? If this new particle, you should have a place for this particle and the so-called particle zoos of standard model. So what you think about it? What kind of particle it could be? What kind of spin, parity, different lepton numbers and so should have. And my comment is all the experiments you have presented can be, we should go of course into details, but I think it can be explained completely different. So there's not unique proof to say we have electron or heavy electron or something like this.
Yes, so thank you for this very interesting question, actually a few questions. What I want to emphasize that I think this is a new particle, it's not an electron. That's why it has a different mass, and I think this bubble chamber track is a rather direct evidence. There was some particle which left this track. We have to understand what is the particle that left this track, and the half-life of this intermediate particle in this track is about 10 to the minus 11 seconds. So it is a very short-lived in the free particle state. Now it always decays into an electron. So it's a lepton particle that always decays into electron. So in that sense, the difference between electron and nuclear electron is something like the difference between the electron and the muon. That's the closest I would say. Regarding direct experiments, it is of course important for a big statement to have as many direct experiments as possible. So what I plan to do in the future is to have more spark discharge experiments, not only with water, but with various other materials dissolved in the water. So what we try to have is various peaks that correspond to various different elements. So for example, if we have copper in the solution, we should see a peak corresponding to the absorption of nuclear electron by copper. If we have zinc, we should see a peak corresponding to zinc. So if we have in these experiments the gamma lines always corresponding to the same mass energy balance formula, that is my plan how to make the conclusive proof.
Can you point with your laser pointer to the track you're talking about?
Yeah, I don't have, I can hear. So there is the decay of the first particle, and this is the start where nuclear electron starts, and it's just the problem is that this pointer often skips the slide. So, and that's the second one, that's the decay into the electron state. So between these two arrows is the nuclear electron, so it's very short-lived.
How many events have been measured in this kind?
So Mr. Nikitin said he had 2 events of this kind.
2 events. So there was no any additional experiments that could confirm this kind of process or not?
Well, this is a challenge,
Yeah,
you know, for experimentalists
No, this is
to
just
be
the
inspired
problem.
and make additional experiments.
No. If you have a new particle, you know, the people usually will start to do many experiments. So I am sure that this kind of pictures or experiments can be, explained differently. You know, there is nothing about. My question is something else. If you have, in your opinion, we have no neutrons, only protons plus heavy electrons.
Nuclear electrons, yes.
Yeah, nuclear electrons. So, what about different? There is a very nice theory of beta decay, not only beta decay, but also all the masses in the isotopic chart. And binding energies. What about it? Because if you are speaking about new particles, you should think about interaction between this composite particle, proton and electron,
Yes.
in the nucleus.
Yes.
So you have charge, electrical charge, and something like isospin numbers. And so I cannot imagine that this kind of particle could exist, because it is really in contradiction to all the things we know. So it is something.
But sorry, Konrad. But do you consider quark to be a thing we know? Because that's why I spent quite a long time in the lecture to talk about quarks. That I don't consider quarks we know. I consider there to be a set of assumptions that lead to mathematical contradiction. I would not say this is a thing we know. Yeah, but actually, but Konrad, I did not make that kind of basic mistake, because in the proof which I referred to, which I can send also to you, it applies the same way whether they are aligned or whether one of them is anti-aligned. The proof applies exactly the same way. So the case that you mentioned is still a contradiction. Well, I can, if you want, we can look at the mass later, and you can show me where the mass is wrong.
Excuse me, what's happened to neutrinos? I don't see any neutrinos in this model. And all these considerations are completely opposite to the standard model of a physical particle that I think everybody knows is working, otherwise is a funny system. And this is my first question. Second question, if you have a bond state with a proton and an electron, you should have a bond force, electromagnetic force. So outside, this is supposed to be a stable system, because it's stable in the lattice. Because it's outside the lattice, I think it's completely unstable, and you have to see the 1 million more radiation gamma, and nobody has seen something like that. Okay, so according to me, I mean, it's interesting and funny hypothesis, just explained in the 1930, and because problem of spin, problem about angular momentum, this model was completely discarded from our actual theory.
Excuse me. It's a question, not.
It sounded more like a comment than a question.
Excuse me. It must be. Excuse me. A moment, please. Excuse me. Is a question or is a lecture? Excuse me. Please.
Okay.
Please.
So the question. So as I understood the question part.
You can speak afterwards.
What happens to the neutrinos? Well, the understanding and characterization of neutrinos was not part of this lecture. So that's a second discussion topic, what are neutrinos, how to understand them. So far, experiments show that neutrino radiation always travels at the speed of light, and we have to understand what makes neutrinos apparently always travel at the speed of light, and why neutrinos are released during the neutron decay. So this we have to understand, but we have to start with a theory that respects the conservation of energy and momentum. So my approach is to respect conservation of energy and momentum, so I don't make any kind of wild assumption of suddenly 80 gigaelectron volt appearing from nowhere. So I think that regarding neutrinos, my proposition is quite more logical than having a completely experimentally unproven hypothesis of 80 gigaelectron volt appearing from nowhere. And in the end of the day, I'm one person, so don't expect me to solve all the problems that 10,000 physicists work on. Thank you.
Sorry, Anders, but
So I propose to close here because
I-
we have problems of time. And so I thank a lot the two lecturers. I think they raised questions and comments and discussion. So it was very, very useful, I think. So I have to close the section. Thank you again. And you can be here in half an hour because now there is the coffee break. Thank you very much. Thank you. See you later.
No, I didn't see here. So here there was nothing. So the nothing. No, nothing. So that's why I had to turn back because here there was nothing. Future use. Yeah, but there was nothing here. Why? I don't know why, but